In this video, we'll discuss counting and technique used for counting. When we refer to counting, we're not simply talking about 1, 2, 3, 4, 5, and so on. This is not the type of counting we're discussing. We're discussing counting that will help us in probability. An example of counting would be if you, let's say, go to a coffee shop, okay, and you will purchase a coffee. In terms of size of coffee, you may have small, medium, and large. And in terms of flavor, you may have French vanilla and, let's say, pumpkin. Okay. So in this scenario here, in terms of if you want to order, what are your options? Well, you could have a small French vanilla or a small pumpkin flavor. Or you can have a medium French vanilla and a medium pumpkin flavor. Or you can have a large French vanilla, or you can have a large pumpkin flavor. So these are all of the choices you have. And if you look at them, you will see that you have a total of 6 choices. Okay? So an easy way or a different way of doing rather than listing them out, yeah, is if you have small, medium, and large. So this you had 3 sizes. Okay, 3 sizes. And here you had French vanilla and pumpkin. Here you had 2 flavors. So notice you could have multiplied 3 times 2, which will give you a total of 6 choices. So you have done this many times already. I mean, probably not from a coffee scenario, but if you look at examples that you have done in a traditional classroom, okay, if your classroom is set up using desk, and there's a space, and you may have another 2 desks over here. So each one of these represents some desk and chairs. And if I ask you how many desks are there, okay? Well, one way to do this is to physically walk around and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's one way of doing it. But can you imagine if you had a very, very large room? This will take some time. Alternatively, what you can do is you can see how many desks you have in that row. And in the row here, you have 1, 2, 3, 4, 5. So you have 5 desks. And then how many desks do you have in the columns? Okay, so you have 1, 2, 3. So here we have 3. And you can now multiply 5 times 3, which will give you a total of 15 desks. Yeah. So what we're really doing here is called the fundamental counting rule. Okay, the fundamental counting rule. And this tells us we can multiply m times n. And what this is really equal to is the number of ways two events can occur. Given that the first event can occur m ways, and the second event can occur n ways. Okay? So what does this really mean? Here's another example that you can think about. Suppose you have an ID card with two character. Oops. Okay. Code. And this consists of a letter followed by a digit. So what we're looking for here, we have some ID card. Okay, let's say this is the ID card. And at the bottom of the ID card, you have a 2-digit. Or 2 characters, sorry. And then the first here is a letter. So here we want a letter. And here it's a digit. Well, if you think about this, in your choices of letters, okay, in your choice of letter, you have a total of 26 choices because you can pick any letter from A, B, C, going all the way up to Z. Okay. And then in terms of your number now, your digit, okay, you have a total of 10 choices. Why? Because you can pick 0, 1, 2, going all the way up to 9. So therefore, you can have a total of 26 times 10, which is 260 ID card with different scenarios you can create. Okay, 26 times 10. Another type of counting we can look at here is something we call the factorial rule. Factorial rule. And before I write the factorial rule, I want to show you the factorial symbol. So the factorial symbol looks like this. Okay. And on the computer, that's generally shift 1. Shift 1. Okay. So what does it really tell us? It's really a multiplication. Okay. but it decreases. So for example, 3 factorial implies 3 times decrease 2 times decrease 1. And you don't go lower than 1, you stop at 1. So 3 factorial is equal to 6. Okay. 1 factorial is just 1. Well, there is an exception to this of 0 factorial. Okay. 0 factorial happens to also be 1. So this one here is a little rule that you will have to remember, because there's no way really to multiply it out, because we say we stop at 1. Okay. 0 factorial is 1. So why do we need, or what is really the factorial rule? Well, if you go back to look at the similar example as we were discussing, right? Example, you want to create an ID card now with, let's say, so how many ID cards can we obtain if we use only numbers now, but with, let's say, 5 characters, and here numbers can repeat. Numbers can repeat. So we'll see what the mean numbers can repeat here. So the first thing to note is that we have 5. So 1, 2, 3, 4, 5. Okay. Now be careful, because in this example also, okay, we're talking about numbers. Numbers. So in your first slot, you can pick 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, each one of these is a choice you can pick when you create your ID card. Okay, so you have a total of 10 choices here. Now, because we say numbers can repeat, once again in this you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you also have 10 here you can choose from. And the same will happen here, and the same will happen here, and the same will happen here. So each one of these, you're going up to 9, right? 9. 0 through 9. Then here you'll have the same thing, 0 through 9. And here you'll have the same thing, 0 through 9. So this means we have 10 times 10 times 10 times 10 times 10, which is 1 and 5 zeros. So we can create 100,000 ID cards. Okay. So now what happens if, if we looked at a similar example, how many cards can be generated if you cannot repeat the digits. So what we're really saying is that you still have 5, 1, 2, 3, 4, 5. Okay. In the first scenario, you could pick 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. So you still have 10 here. But let's assume that you had used a 3. Okay. So what we're saying that in our ID card, the first digit is a 3. Okay. Now you cannot repeat. So in the next time around, you have 0. Okay. You have 0, 1, 2. You've used 3, 4, 5, 6, 7, 8, and 9. I left out my 7 over here. Okay. So let's say this time around you've used 0. Okay. So, but notice that in here I don't have 10 choices anymore. Here I have 10 choices. Here I only have 9 choices. So this number becomes a 9. And the number we picked was 0. Okay. The next time around we do this, we only have 1, 2, we've used 3, we've used 0, 4, 5, 6, 7, 8, and 9. So in this case here now, we only have 8 choices. Okay, so let's say we decide to pick 9 now. Okay, so the number we've selected is now 9. Right? But here we have only 8 choices left. So every time we choose a number, okay, every time we choose a number, the next time around, the number of choices decreases by 1. And that's where we have this part here, cannot repeat. Okay. Meaning there's nowhere in this code that if you use 3 the first time around, 3 cannot appear here, 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 or here, because we've already picked 3. So let's finish this up. So we've picked 3, we've picked 0, we picked 9. So we still have the choices left 1, 2, we've picked 3, 4, 5, 6, 7, and 8. And if you look here, you should only have 7. 1, 2, 3, 4, 5, 6, 7 choices. Okay. Well, let's assume this time around I picked a 2. Okay. So we had 7 choices here, and the number we selected here is 2. Okay. Then the next time around we do this, we will only have 6 choices. 0 is gone, so we have 1 left. 2 is gone, we picked 3 already. So we have 4, 5, 6, 7, and 8, because we used 9 already. So if you look here, we should only have 1, 2, 3, 4, 5, 6 choices. And let's say here we decided to pick, oops. So here we've decided to pick the number, let's say 5. Okay. So we had 6 choices, and the number we picked was 5. So 1, right? So realistically, we had 10 times 9 times 8 times 7 times 6. And if you multiply that out now, okay, 10 times 9 times 8 times 7 times 6, that would give us 30,240 ID cards. So notice there is a big difference, okay, in the total. Big difference. Now, what if I ask you the problem? What is the probability of choosing an ID card with code, okay, with the code 30925 from the above example? From the above example. Okay. Well, the probability here, okay, we know that total cards we can have, total ID cards, and how many created, let's say, and how many will have the given code. Well, we calculated this. We know that the maximum ID cards we'll have is 30,240, right? This here is the maximum ID card we'll have. So that's what goes here. But how many cards can have this security code? Well, since digit can't repeat, there is only one that will have that security code. Yeah. So we'll only have one out of 30,240, which is a very, very small probability. Okay. So that's why we need to really learn counting, because the counting scenario will help us. Yeah. We're able to find probability if we know how to count faster. Another type of counting that is very, very common is what we call the permutation rule and combination rule. Yeah. Permutation and combination is two ways of counting, and we usually say where order matters and order does not matter. So when we say order matters, right? So what does that mean for permutation? Yeah. Permutation of items arrangement in which different sequence of the same items are counted separately. Okay. So what do we mean by that? So for example, let's say we have three letters, A, B, C. Okay. Now the arrangement that I can have here, this can be arranged, well, we can have ABC, obviously, or we can have ACB, or we can have BAC, or we can have BCA. We can also have CAB, and we can also have CBA. So here we should have a total 1, 2, 3, 4, 5, 6 of them, 6 ways. Yeah. And each one of them are counted separately. Okay. Count separately. Each one of these, okay, each one is counted separately. And the reason we say separately is because ABC is totally different from ACB. Although it's the same 3 letters, okay, the arrangement, we count them separately. So this is permutation, right? This is where we say permutation. Now, in a combination scenario, okay, in combination, okay, of items are arranged, or arrangements, in which different sequence of the same items are not counted separately. Okay. So once again, if we have our example A, B, C, okay, the arrangement ABC, ACB, BAC, BCA, CAB, and CBA, these here are all considered to be the same combination. Okay. So therefore, the number of ways here is just 1, whereas the number of arrangements for permutation was 6. So if we look at the permutation rule, yeah, there is basically a formula, and the way we write it is N permutation R. These are like lowercase or small letters to the bottom of the P, sort of like a subscript. And this here is the formula. This is N factorial divided by N minus R quantity factorial. Okay. So what is N and what is R? Okay. N represents the different items available. So N represents the number of different items available. So we've we've talked about n when we started in earlier chapters, right? The total. R, okay, R here represents your selection. So R represents the selection from N. The selection from N. So what we can say here, for example, okay, if you have 5 letters, okay, and let's say letters are A, B, C, D, and E available, and 3 of them are to be selected. Okay, without replacement. Okay, so in this case, N would be 5 because you have 5 letters, and R will be equal to 3. Okay, because you want 3 of them are to be selected. So R can never be bigger than N. R can never be bigger than N at all. Okay. And we'll do examples of these in a few minutes. So this was the permutation, okay? Permutation rule. Now, if we look at the combination rule, okay, combination rule, the combination N combination or choose R is now equal to N factorial divided by N minus R quantity factorial times R factorial. Okay, this is a times. So as you can see, the combination will be a smaller number because the denominator here was larger. Okay, your denominator here will be a larger number because you're now multiplying this by an additional number. And N and R is the same. Okay, N is the same as we said over here, represents the number of different items available. Okay, so we're getting that from here. Number of different items available. Okay, and R, as we said from here too, is the selection from N. So these two formulas is on the formula sheet given, or they're easy to look up online, so you can always look them up and see what they are, or you can learn them. Now, they will be very important because in a preceding section, when we start looking at the binomial formula, you will see that one of these formulas will reappear in part of that formula. So let's look at this example here. So here we have a lottery game, and we have to select 5 numbers, okay, that must be drawn. So we want to look at 5 numbers. So numbers are selected 1 through 39. Okay. And you could pick any 5 different. So now notice here that this will be a combination because the order which you select them doesn't matter. When you select a lottery number, the order doesn't really matter in this case. And it tells you order does not. So I'm saying that because it tells you here order does not make a difference. Okay. So the question, or the big question here, is what is n? Or even before I get that, since order doesn't matter, we will use combination. So we're going to use NCR, which we know is n factorial divided by n minus r factorial times r factorial. So the question is, what is n and what is r in this scenario? Well, we're choosing numbers from 1 to 39. So that includes 1 up to 39. So n here will be 39. And we have to select, okay, you select 5 numbers. So r here would be 5. Okay. So the way we write it is 39 choose 5 is equal to 39 factorial over 39 minus 5 factorial times 5 factorial. Now these numbers are large, so you will need a calculator, okay? So using my calculator, 39 factorial is a very, very large number, yeah? Extremely large. So the numbers are very large, but in event you will get 39 factorial over 39 minus 5 is 34 factorial times 5 factorial. Okay. Now because you're doing a division, this will end up to be a smaller number. So punching in the numbers in your calculator and working them out gives us a total of 575,757 choices you will have. So remember the question, how many different lottery tickets are possible? So if you're only choosing from 1 to 39, okay, and you're picking 5 numbers, you have a total of 575,757 choices. Yeah. Now, I could also go on and ask you, well, what is the probability of selecting the winning ticket? Okay. What is the probability of selecting the winning ticket? So let's say I ask you a part B to this. What is the probability of selecting the winning ticket. So the probability of winning, we know that the total number of choices is 575, 757, but there is only one winning ticket. Okay, there is only one. So here's another example that we can do. So you want to appoint 3 officers. Okay, we're looking to appoint 3 officers. And the 3 officers we're looking at is the Chief Executive Officer, the Executive Chairperson, and the Chief Operating Officer. Okay. Also, there are 8 qualified candidates. So in the first scenario, well, whatever the question is, we don't even know. We know that N is equal to 8. And we also know we want to choose 3 people. Okay. Now, if you look at part A, okay, how many different ways can the officers be appointed? Well, these are officers. You're picking people, so does the order matters? Okay. Question here, it's like the same as a presidency, right? Do you get the president first and then get the vice president, or do you pick the vice president first and then vote for the president? Okay. So order does matter here. Order matters. Why? Because you should pick the chief executive officer first before you pick anyone else. The president of the company has to be first. So in this case, we'll use NPR. Okay. And the formula we know is N factorial divided by N minus R quantity factorial. So here, N is 8, so 8 permutation R is 3 will be 8 factorial divided by 8 minus 3 factorial. And that's equal to 8 factorial over 5 factorial. Sometimes these are easy to work out in your calculator, okay? Because if you don't have a calculator, well, let's get the number on the calculator first. 8 factorial happens to be the number 40320. Divided that by 5 factorial is 120. And if you divide those two numbers, that is 336. Okay, so how many different ways can the officers be selected? 336 ways. Now I want to point out something to you. This can be worked out, because 8 factorial really means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And 5 factorial is 5 times 4 times 3 times 2 times 1. And from your regular arithmetic, you know that these numbers can be reduced with that numbers when it's multiplication. So all you're really left with is 8 times 7 times 6. And if you multiply 8 times 7 times 6 in your calculator, you will get 336. So sometimes the numbers can work out easily in a calculator, okay? Now the second part to our question, yeah, the second part to our questions is how many different ways can a committee be appointed? How many different ways can the committee be appointed? So the big question here, once again, is does order matter? Meaning, for example, can the president be in the committee? The vice president, can they be in the committee? Yeah. So that's a big question that we have to ask ourselves. So in general, or generally speaking, the president can be in a committee. And obviously order doesn't matter here. If you pick the president first, okay, so you have, I mean, think of this scenario, right? You have 8 people. Okay, and one of them here is the president. So you put these 8 names in a bag and you shake it up. Okay, it doesn't matter who you pick first. Okay, so if one is the president, as we were thinking about, one of the president, okay, or the CEO, okay, and then we have the COO, it doesn't matter. When you put these names in a bag and you shake them up, the order does not matter. So when you're picking committee members, the order in which you pick the committee members doesn't matter. You may vote later who's the head of the committee, but the order in which you choose the member doesn't matter. So we will use combination. And the combination formula, NCR, is n factorial divided by n minus r factorial times r factorial. Yeah. So how many committee members did we have to pick? Yeah. How many different ways can committee members be appointed? So if you notice here, okay, it must also be applied to with 3 different members. So planning committee happens to be 3 also. So this 3 has nothing to do with the 3 executive officers you choose. So in this scenario, N is still 8, but R happens to be 3. Okay, this only happens because the committee members happen to be the same as the executive officers, right? The number of people is 3. So 8 choose 3 will be 8 factorial over 8 minus 3 factorial times 3 factorial, which is 8 factorial over 5 factorial times 3 factorial. And that becomes, well, we knew from before 8 factorial over 5 factorial is 336. Yeah. But if we work this out, 8 factorial, we knew from before, was 40320 divided by 5 factorial we knew is 120, right? But we're multiplying this now by 3 factorial, which is 6. So this becomes 40320 divided by 120 times 6 will be 720. And this here, 40320 divided by 720 is 56. So you have 56 ways, okay? How many different ways can committee be appointed? You have 56 ways to set up the committee. 56 ways. So there's an example. It's very similar to the one we've just worked. Try to see if you can do this example. And there are many more examples that you can try from what will be assigned for homework. Yeah. So try this example and we'll work it out the next time we meet.